So once again, my name is Lesa Tran. I'm super excited to be here this afternoon. And so great to see such a diverse group of individuals interested in learning about chemistry, but probably most interested about food and cooking. But usually when I start talks about the chemistry of cooking class that I teach and have been teaching for the past 10 years, I always like to kind of get a survey of how we are in this group, who is actively engaging and listening to this, this presentation. So a quick survey before we start. By a raise of hands, I'd like to know, across the group, how confident do you feel in the following things? How confident do you feel in the knowledge of chemistry? Be honest. Dr. Weber, clearly. Yeah, good, all right. Yeah, about like 10 people, and that's understandable. What about your chemistry laboratory skills of those individuals? Oh, actually more individuals have their hands up there. Okay, that might actually show something that is really interesting that I'll talk about very soon. Now let's switch gears and have a conversation about, like, what about your kitchen skills? Yeah, a whole lot more individuals are raising their hands. And then the last one that I want to ask is, how confident do you feel in your ability to eat and enjoy food? And I hope it's everybody, otherwise I cannot be friends with you. So I hope this goes to show and kind of sets the tone of the reasons why I came here today, the reason why I've been teaching this class for the past 10 years, the reasons why I became a teacher all along. So just to start off with really quickly, to tell you a little bit more about myself, John did a fabulous job talking about my professional history. But I want to start back from the origin of, where my family started. So I am a first-gen low-income child of an immigrant family. From Vietnam, and I actually speak Cantonese Chinese at the home, so I'm kind of mix of Chinese and Vietnamese. But I've been in the Houston area all my life. So I was born and raised in Houston, went up through the Fort Bend ISD system out in Sugar Land. And all the while, my immigrant parents worked up the food industry chain. Started off as a convenience store owner group, and then they worked their way up to actually own a fortune cookie factory for 15 years here in Houston. That got me really interested in cooking and food, because I was surrounded by that all the time as we delivered fortune cookies to restaurants in the Houston area. But then as I went through schooling, I realized that as much as I loved cooking and I loved to learn about science, I always struggled with reading as an ESL student, but also just, it's really passive, really boring stuff, at least for me personally when I was growing up through school, right? I really struggled with attention, with being able to connect with the material that I was learning in class, or was supposed to be learning in class, which has really inspired me to really think hard about the way that I teach now as an instructor at Rice. And so now that I have a family of my own of 2 small children, the oldest being, just started 2nd grade, at Rice, I've really gotten really involved with developing new ways to teach in an active way. And it started, not only as a student, so I've never left Rice. I got all 3 of my degrees in chemistry at Rice. Started as a teaching faculty member in 2012, and I worked my way up, and now I am, running a biosciences and bioengineering institute, where I'm connecting individuals from across campus to talk and learn and collaborate with one another in the bio-related fields. And on the teaching side specifically, I try to find ways to connect with students, to bring them together to actively engage in the materials. And specifically in the undergraduate world, I am all about teaching science as how science is done. Think about that for a moment, because typically in a science class, probably in grade school, you probably remembered being assigned some chapters, you read it overnight. Chances are you did relatively well the next day on a quiz, right? And rinse and repeat. It was just memorizing, applying. That's a form of deductive reasoning, right? Applying that knowledge to a context. But science, in many ways, is really focused on the process of inductive learning, right? Collecting information, manipulating it, trying to grapple with it to try to understand what can you extract out of that experience or those observations. So hands-on and experiential learning is where it's at. So how can we play that into the way that we teach science at Rice specifically? And so as John said, for the past 10 years, I had been involved in turning general chemistry, which we have about 450 students enrolled every year, sit around tables of 6 and engage with data, actually are given sets of data that John Dalton himself collected in gas volume data to derive how he knew that atoms exist. Rather than reading it in textbooks, have the students walk through the data and feel excited that they too can do what the forefathers and foreparents of chemistry did, decades, if not, centuries ago. And then specifically in the chemistry of cooking, trying to relate to others in a context, as we all saw in the raise of hands, in something that everyone can relate to. Everyone needs to eat. Most people enjoy it. Most people enjoy cooking too. So how do I use that medium to engage my students to learn some pretty tough chemistry? So it's chemistry, like hardcore chemistry in disguise of really, really fun stuff. And in our class, it's just as much of a science class as it is a culinary class. We meet on Mondays, we have theory and lecture. Wednesdays, we have a kitchen that is open to us to demonstrate and bring to life all the concepts that we covered in theory. And I'm happy to talk more about that later on. But for the purpose of today's talk, I wanted to set the tone of what exactly is the chemistry of cooking, and one way to do it is to just look at dictionary definitions of the two words, right? The way that I'd like to define chemistry is the study of stuff, right? Stuff is all around us. We get to study what stuff is made out of, how stuff interacts with one another, understand their properties and reactions. Well, cooking is kind of just that, right? It's the manipulation and the preparation of food, which is stuff, and how they interact with each other, how they're perceived by individuals. So in other words, when I think of the chemistry of cooking, it's another fun way to understand the natural world and to think like a chemist. So what do I mean by that? Again, in grade school, you probably learned about the scientific method, right? You start off with a hypothesis, you do some experiments, draw some conclusions, you develop a model, go on and be happy with it, right? And develop the knowledge of science and chemistry in specific. But how do we apply that to cooking? So I'm going to take baking biscuits as a good example. So perhaps you might want to ask yourself a question of, how do I make the perfect biscuit? Then you do some background research by eating a whole lot of biscuits, making some observations, and then you can form a hypothesis of, well, perhaps the temperature of the fat source, like butter, might affect the flakiness of the biscuit, which I really want and desire. So you would conduct some experiments, say vary the temperature of the butter, whether you have cold, room temperature, melted butter, and make a lot of biscuits, eat some more biscuits in the name of science, and then hopefully develop a model that perhaps you could draw a conclusion that, yes, cold butter does contribute to flakier biscuits. But then if you are engaged enough and more curious, then you might likely ask yourself even more questions, like, what if I were to use lard or shortening instead of butter? Or what if I were to change up the flour type? How might that change up the texture or the outcome of the biscuit? So it's a wonderful thing that I've taken advantage of in the chemistry of cooking class. And this is a nice photo where every single lab group has a different variable that they're responsible for to change up in a base recipe. And they all bake it off. And at the end, they all get to do science and eat up a whole lot of biscuits and draw some conclusions from it. So even though I don't have food today, I'm really sad that I don't, hopefully I can at least walk you through an experience of what you might get in a class like mine. All right, so another way to think of the chemistry of cooking is perceiving recipes as chemical reactions. So if you learn a little bit of chemistry, chances are you have recognized that in chemistry, we must not only identify the amount and the type of molecules or reagents there are in a chemical reaction, just like in cooking, you have to identify the recipe and the ingredients and how much of the ingredients there are that you need to put into the dish. Side note here, always, always, always measure by mass and not by volume, because we learn in science that mass is conserved, volume is really highly variable depending on the condition and the way that you measure. So pro tip as a cook, always use mass if at all possible. The other thing that we like to do as scientists is, again, observe how those materials interact with one another. So take, making a biscuit. When you cook or bake your biscuits, you're applying energy. You're applying energy to your biscuit dough so that the starch molecules can interact with the butter molecules, which can interact with the sucrose molecules in your table sugar. All of that can be manipulated to get you to your desired outcome, or in other words, a product in a chemical reaction. So there's a lot of parallels in the way that scientists perceive the natural world, just as how cooks perceive their foods that they cook in the kitchen. And just like how scientists can control the various things that or the variables that they identify in an experiment, cooks also have the ability to control the amount of ingredients that they put into their recipes, how they cook, how long they cook, how intense the heat is. All of those things, as long as you understand every single aspect of the recipe, makes you a smarter cook, because you'll have greater appreciation and a greater sense of control in getting the desired outcome that you want. All right, so now switching gears, we're gonna get into the chemistry stuff now. All right, so as I said, the first thing to take note is we have to identify the types of molecules there are in food. And it turns out that there are 4 basic types of food molecules that are very conveniently summarized in all of the nutrition facts labels that we see in the backs of the packages of the things that we consume. So I'm going to highlight them. Right, the first ones, hopefully you all can see that, are lipids. Lipids, fancy name for fats. Next are carbohydrates, like sugars. Next are proteins. The last one is water, and it turns out that nutrition facts don't document how much water because of the way that they're analyzed. They actually dehydrate the food, so they eliminate water. But then, as you can see on the nutrition facts, there's other substances like inorganic compounds like metals or vitamins or cholesterol, for instance. Those are known as organic molecules. And those are all usually in minor contributions, so we're really just going to focus on those top 4. Another fun fact as a scientist you can think about is that perhaps you can actually calculate the caloric content of your foods just simply by knowing what's in it. That makes sense. That's where they get the calculations from on these labels. So if you memorize the 944 rule, you could test it on the different things in front of you or as you're eating lunch, that if you know how much fat, carbs, and proteins there are in your food, all you need to do is multiply their gram value, their mass value, by 9, 4, and 4 respectively to give you a pretty good approximation of how many calories there are in the food itself. So if you see and look at this really closely, right, there are about 17 grams of fat, 54 grams of carbs, and 3 grams of protein. If you do those multiplication steps, then it should total to about 381 calories. I have strategically hidden the total value of calories in the nutrition facts, and funnily enough, it is pretty darn accurate. So check it out. Try to challenge yourself to see whether nutrition facts follow the 944 rule. Okay, so those 4 basic food molecules are what makes up all the food that we eat. So we're going to walk through each one of these and kind of highlight their unique properties. But before I begin and focus on each one, I want to actually highlight that even though each one of these categories of food molecules are quite different, they are made and broken down in the exact same way. Isn't that really fascinating? That lipids, proteins, carbohydrates, there are very different types of molecules, but in chemistry they follow very, very unique structures in the processes of how you assemble and disassemble them. So regardless of whether you're looking at lipids, carbs, or proteins, we can look at those molecules as what we call macromolecules. In other words, they are long chains of single units that are linked up with each other, kind of like a strand of pearls, if you will. And depending on the type of molecule, they have different units or monomers that make them up. And you'll see that in the next couple of slides that I will use to present about each of these types of molecules. And as I said before, the formation and the decomposition of each types of these molecules is not only identical, but also reversible, which is really fascinating too. So you could build up proteins, you could build up lipids and fats in the same way, in the opposite way as how they are broken down. All right, so let's get into it. Lipids. I'm trying to keep this short in terms of what you need to know about the lipids. So lipids, we know that they're fats, and chances are you've heard of the term triglycerides. Well, the reason why it's called triglycerides, as I said, is that it takes 3 fatty acids in a glycerol molecule and they link up, right? So think of the monomers linking up into a polymer, and that is why it is called a triglyceride. Lipids, as we know, don't like water. That's why we call it hydrophobic. They don't mix well with polar molecules like water. And depending on the composition and the types of fatty acids that link up to this glycerol molecule determines whether they are solid or liquid in room temperature. So we call fats solids like butter. Butter is considered a fat, whereas oils are considered liquids at room temperature, and it's simply because of the way that these fatty acid chains are composed and how they are arranged spatially. In other words, unsaturated fats are due to the fact that these fatty acid chains might actually have a bend or a kink to them, so that spatially speaking, for those who are really good about spatial recognition, in 3D, if you have many of these types of molecules packed in a volume, it's less dense because they take up more space, right? And less dense substances usually are liquids at room temperature, as opposed to more dense substances are usually solids. So that's some really neat phase transition and phase states concepts going on here with lipids. Next up are carbohydrates. Carbohydrates, many times we think of sugars. And so technically we call them polysaccharides because they are made up of many monosaccharides that link up together. So monosaccharides include glucose, fructose, and galactose. You can link them up in pairs to make things like sucrose or lactose or even maltose, it turns out. Or you could continue linking them all up to make polysaccharide molecules that look a lot more complex, like starch molecules or glycogen or cellulose. Probably you've heard a lot about that stuff in plant biology. And as opposed to lipids, carbohydrates love water. If they aren't water soluble, then they love to retain water, even though they might not dissolve in it. And their primary function in nature and in the way that we consume them is that they either provide energy for us, which is why we love carbs and eating carbs, but it also provides structural support in the plant sources that they are derived from, or the animal sources that they're derived from too, technically. All right. Next category are proteins. Proteins, another example of polymers, but in this case, the single units are amino acids. In biology, you probably learned that there are 20 commonly found amino acids that are encoded by the human genome, and depending on the way and the arrangement that you link up these amino acids, you can create what we call a protein. Proteins are generally water soluble, not all of them, but most of them are. And what's really, really important about proteins is that the structure of the protein, the way that they're linked up, and how they're arranged spatially, if they even have like little coils or sheet-like structures within this protein model, dictates how they function. So with the structure comes the function, and you gotta think about this very, very carefully because every single protein has a function then, especially enzymes. You might have heard of enzymes. Enzymes are proteins specifically that have a very, very set function. And if you destroy their structure, you destroy their function. And that happens all the time in cooking, when you think of it. This is known as denaturation. Denaturation is the process, it's quite irreversible, to change the protein structure and function upon a change in heat, or a change in pH, or a change in salt concentration around it, or even the way that you have added energy to distort the way that they are spatially arranged. And when you denature a protein, they will unfold and then refold into this really amorphous, unusable form that loses the function of that original protein. A really great example in cooking are eggs. Eggs have a lot of protein to it. In the raw state, it's quite translucent and bright yellow with a center with a yolk. But depending on whether you heat it up or you whisk it or you add some base or lye to it, or expose it to salt, you can drastically change not only their appearance, but also the taste and the texture, and as well as the function of the egg itself. All right, so denaturation is really important, and the longer it actually is exposed to these extreme conditions of changing pH and salt concentration and heat and whatnot, the more denaturation happens. So I'm going to pause because I love active learning and inquiry-based learning and give you all a quiz. Trust me, it's not terrible. Really, really relatable context for those who like cheese and who like burger patties, right? So what I had my students do was that they made homemade ricotta cheese using whole milk, which has a lot of protein in it, and then all beef patties, a lot of proteins in it. And in this experiment, they made ricotta cheese by exposing the milk to an acidic source. There's lots of acidic ingredients like lemon juice, vinegar, even buttermilk, I think, is one of them, right? And on the right-hand side, the way that they made the burger patties they wanted to see is whether the time at which they add salt to the burger meat impacts the overall texture of the burger patty. Okay, so I want you to spend a couple of seconds, turn to your partner next to you to discuss, can you match which acidic ingredient is used to make each one of these types of ricotta cheese, and then similarly, which of these patties correspond to when the salt was added to the meat, before grinding, after grinding the meat, or right before you cook it. So take a moment. All right, just a few more seconds. Lock in your answers. You're going to turn these in for a grade. That's how it works, right? That's how it works. Nice, awesome. With the instructor right next to them, too. High pressure. Well, who wants to volunteer their answer for the ricotta cheese? Who would like to volunteer to go through their answer? Yeah.
Honestly, I think that B would be the buttermilk.
Okay.
That A would be the vinegar because it would be slightly less acidic than lemon juice.
Yeah.
C would be overactive and B the lemon juice.
Good. I like the trend. I like how you've actually ordered it. Anybody want to counter? Yeah, of course you can challenge.
Awesome. So I think that buttermilk is the first one. A is buttermilk, B is vinegar, and C is lemon juice.
Okay, so how many of y'all think, it looks like B is the most contentious, like the firmest one, right? By raise of hands, who thinks that's vinegar? Ooh, brave souls. All right, who thinks that's buttermilk? Okay, who thinks that's lemon juice? Okay, not many people think it's lemon juice, but that's okay. All right, so let's talk about this really quickly. I appreciate that there are, we all kind of agree that B is a very extreme condition. Chances are it's either experiencing a whole lot of denaturation or not at all, right? And so what did we say? We say that the more denaturing happens, that means the more acidic source is actually exposed, or the longer it's been exposed to extreme condition, which really causes them to clump up, right? So let's show it. So it turns out that the softest one, down at the very bottom, is made up of buttermilk, or made from buttermilk, because it is exposed to the least extreme of the pH levels. pH is on a scale of 1 to 7, or 0 to 7 technically. Lower is more acidic. So buttermilk is the least acidic of those ingredients, which will have the mildest flavor and also the softest of the ricotta cheeses, as opposed to vinegar, which is the most acidic of the bunch, causes that cheese to really clump up. Isn't that fascinating? All right, let's try the burger patties now. Who wants to volunteer their answers for the burger patties? What is the order of the patties by which salt was added to that meat? Who wants to? I'm going to pick on somebody else, but mental high five there. Thank you for volunteering. Yeah. Yes, please.
A looks like it was before grinding the meat up.
Uh-huh.
B looks like it was. It looks chronological.
it looks chronological. The answers are as how they're lined up top to bottom, and you're absolutely right. Yep. So the longer the salt sits with the protein, kind of like the longer the acid sits with the cheese, the more compact it is, the harder it is. That's why the top one kind of looks like sausage for those who eat sausage. Like, I'm going to remove that. It's really smooth, right? It's because sausage is made from curing, and curing is just a whole lot of salt added to the meat. And so that's why that texture comes out the way that it is. Isn't that really cool? You could even do some chemistry inside your own kitchens and try this out. Not too expensive to do. All right, last of the bunch, water. The most important substance in our bodies, right? It makes up about 50 to 60% of our body. And it's extremely polar. It's a great solvent, meaning that it dissolves a whole lot of things that are polar as well. And it's all due to the fact that it's tiny, there's only 3 atoms to it, and it's bent. And that is what makes it polar. There's a negative side to it and a positive side to it. And so when these molecules are interacting, that's a nice simulation of what it might look like, that those molecules can move freely, but have many opportunities to interact with one another because of its geometry and its polarity. All right. So I'm going to switch gears now. Using all the things that we just learned in the 4 types of food molecules, instead of talking about biscuits, 'tis the season, right? It's fall, y'all. Let's talk about apple pie. Everybody has a different definition of what makes something perfect because it's all to the eye of the beholder or to the taste buds of the taster, right? So rather than tell you what I think is the perfect pie, I'm going to restructure this as what things should you consider in order to make your perfect pie. Got it? It has everything to do with science and chemistry, and as long as you have control and manipulate those variables quite carefully, you can very likely get the outcome that you want from your apple pie. So for this talk, I'm going to hone in on 3 different factors that I think most cooks think about when they make apple pie. The first being the crust. I think it's very heated, very, very debatable as to what type of crust is considered perfect, but we're going to walk through what makes a crust first and how do you achieve the perfect crust for yourself. So for those who don't bake, I'm going to walk through how you traditionally make pie crust. I bake a whole lot. I love doing this stuff, and I'm always happy to share how to cook things with other people and talk science, of course. But the way that you do it is that you take your dry ingredients. It's mostly flour, a little bit of salt. You whisk it up together, and then you take some cold butter and you cut it in, meaning that you just kind of slice up and dice up the butter into tiny pieces, and you mix it in with the flour mixture. And then once you do that, you add just enough water to make that dough form. Not too wet, but just wet enough to have a clump. And you let that dough sit in the fridge for a little bit, and then when you're ready, you could roll it out, put it into your pie dish, and you're ready to rock and roll. Okay? Pretty straightforward, right? Pretty simple. There's only flour, there's butter, and water. Those are the only 3 ingredients, and of course salt, but we'll talk about, we won't actually talk about salt, we'll talk about those first 3. Okay? So, as I have done before, let's talk about flour specifically. What is it made out of? Well, it's made mostly of starch. Starch is a form of carbohydrate. It provides a lot of structural support that we had talked about previously. And so it all comes from wheat when we talk about all-purpose flour, for instance. There are other sources of flours that you can now get at your local stores. But primarily when we talk about flour, it usually comes from wheat. And it's made mostly of starch and about 10 to 15% of proteins and a tiny teensy bit of fat, it actually turns out, but it's negligible. But even though starch is the most prevalent substance in flour, it's actually the proteins that make it really interesting. So those 10-15% of protein content is what determines the overall structure of your baked good at the end of the day. It's so important, in fact, that pastry chefs have developed a system to define whether or not flour have high versus low protein content. And they call them hard versus soft flour. So take at the very, very top there, bread flour is the highest of protein content, around 12 to 14%. That provides a lot of structure to your bread per se. On the opposite end, cake flour provides delicate textures for cakes and sponges. So that corresponds to lower protein content. But the reason why a lot of people love to use all-purpose is because it's in a happy medium, right? It's quite forgiving depending on what you want to make. And the reason why the proteins are so special is because they make what we call gluten. So specifically, there are two types of proteins in flour, known as glutenin and gliadin. When they are mixed together in the presence of water, they form this really cool mesh-like network when you mix it or you knead it in that fashion. So the gliadins kind of look like ball bearings. Glutenins look like little silly string. And when they're mixed with water, water is really important. That's super crucial to have. They can interact and bond with each other to form this mesh-like network. And you could even pop it into a scanning electron microscope to kind of see the formation of gluten. Isn't that kind of cool? That depending on how long you mix or knead the dough, you can have under-kneaded dough where you could actually see not very strong fibers or gluten being formed. Kneaded definitely looks very elastic, right? But then you can also technically over-knead your dough and it looks quite broken compared to the middle image. So again, the most important part to flour is the protein because it makes gluten. And to make gluten, you need the protein, you need water, and you need mixing, okay? The other ingredient is butter. Butter is not water, right? It has a little bit of water, but it's made mostly of fat. We call this an emulsion because we know that butter and water don't mix together, and any type of substance that forces those things together is known as an emulsion, kind of like salad dressing, if you will. That is an emulsion as well, or mayonnaise. It is mostly fat, 80% of it, and since it's not water, it actually inhibits the formation of gluten, if you will. The 18 to 20% content of water in butter does technically contribute to gluten formation as well, but not so much. Rather, it provides a really great source of steam. We'll talk about that in the next bullet. The last bit, the 2%, is milk solids. That's protein and sugars. And that, even though it's in a minority, is probably why we love butter so much, because that's where all the flavor comes from. But going back to water, the very important aspect about butter is the small bits of water that it could contribute if you distribute that butter within that crust in tiny different flakes or different pockets, because when you bake that crust, that butter will melt, the water in that butter will steam and will puff up and make little pockets, and that is what makes those yummy, flaky goodness that we love in crust, right? So isn't that kind of interesting that flour actually is dependent on protein, even though flour is made up of carbs primarily, and then butter, even though it's made out of fat. The important part is actually water, at least in terms of the pie crust. So it's all really, really cool stuff that we're seeing here. So to summarize, doing well on time. If you want to make a perfect pie crust, your perfect pie crust, depending on whether you want to make a more dense and crumbly crust or a tender, flaky crust, there are various things that you can adjust, right? So we're going to go down each one. Anybody want to try the first one? How would you change the protein content if you want flaky versus dense? Yeah.
You might want to use less protein if you want more dense crust.
Less protein actually is when you want more dense, because protein makes more gluten, and gluten gives more structure, right? And it'll be much more dense like bread, right? Yeah, very good. But I'm glad that you're thinking about the protein content, because that will dictate the structure. What about the temperature? If you want tender and flaky?
You want higher for dense and lower for tender.
Good, yeah. So butter should be colder if you want flakes and tenderness, right? Melted butter is usually good for your cheesecake crusts, for instance, that are pretty dense. Water, right? We talked about this. Water is really important in making gluten. So if you want to limit gluten formation, you limit the amount of water that you put into it. Otherwise, you put a whole lot of water, more gluten forms, the more dense it is. The less you manipulate it and mix it, the more tender it is, right? That's all about gluten formation. And then dough temperature, kind of like a butter temperature, the lower the temperature, the more tender it is because you will manipulate it less. Got it? Questions there? Okay, so that's the first one. The other two are really short. Next one is apple type. Also highly debated in the baking world. So many different types of apples out there that contribute to different flavor profiles as well as textures. And so how do you make pie filling? If you don't know how to make pie, you just slice some apples, mix it with some sugar and spices and maybe some cornstarch for some thickening agent, and then you just dump it into the pie and put it inside the pie. That's the most primitive way to make pie, okay? But again, we want to cook smarter. We want to achieve the ideal texture and flavor, so how are we going to do it? Again, let's talk about apples. Apples are the primary ingredient here. They're made up of mostly water, 85% water, but the remaining composition is coming from the plant cells, right? Even though plant cells have a lot of water and some air to it, the plant cells are made up of a whole lot of carbohydrates, specifically cellulose and pectin. Think about cellulose as fibers and pectin as the glue that keeps these little water balloons of plant cells together. If you destroy the pectin or melt the pectin or destroy the cellulose in any way, those little plant cells burst, release the water, you get a really, really hot mess of liquidy goo, okay? So when it comes to making apples or cooking apples, if you cook it at a high temperature, that will melt away or decompose your pectin specifically. Water will also steam from the apples as well, as in addition to air expanding. And you'll have a hot mess of an apple pie, at least this is what I think is a failure, right? Sorry, I'll be honest. And specifically what happens is that in addition to having watery filling, because again, the plant cells have exploded, mushy apples because the pectin is not really keeping those apples together anymore, but that air expansion from the plant cells contributes to this gap, this pie gap, that is usually not aesthetically pleasing when you make pies. Ideally, you want that pie filling to fill through and through from top to bottom, and you usually don't want a gap there. And that has everything to do with the air inside the plant cells. So how are we going to address each one of these challenges? What are ways specifically to slow down that pectin degradation? Well, it turns out that Kenji Lopez-Alt, which is a really popular food writer, set off and baked a whole lot of apple pies. I think he took on 10 different apples, used the same recipe, just changed up the apple type. I only show 3 here, the most common probably, that are most visually different. You got the Red Delicious being the sweetest, Granny Smith, which is usually the tartest or the most sour, and then Golden Delicious is kind of a happy medium. And looking at those photos, you can actually see that there's a trend. There's a trend in the texture of the way that those apple slices are inside the filling, right? It kind of goes from left to right, mushy, to more structured. It has everything to do with the acid content in the apples, because acid slows down pectin degradation. It turns out that due to multiple chemical reactions, in addition to slowing down that degradation process, it actually helps strengthen the pectin network as well. So in addition to considering the flavor profile that you want, you have to pay mind to how that acidity level might affect the overall texture. But what if, I want it all? I want somewhere in between, a happy medium of sweet and sour and really firm. Because Golden Delicious apple pie up here looks good, but it's not as firm as a Granny Smith. But what if I like really firm filling? Can I achieve that? Turns out you can, right? Well, if you actually par cook the apples at a low, gentle temperature, you activate an enzyme, a type of protein, remember? That is, its sole function is to strengthen the pectin network, that around 120 to 160 degrees Fahrenheit, well below a baking temperature of 350 degrees, right, in the oven, you can strengthen those pectin molecules by what we call cross-linking with calcium ions, and that will cause them to retain its apple structure even though it's tender enough to eat. So the solution, if you're engaging in apple pie baking this season, just slice up your apples, toss on top of it a couple of cups of boiling water, cover it and let it sit for 10 minutes. That's gentle enough heat to activate those enzymes, strengthen that pectin within those apple slices. You can even see air bubbles dissipating from the apple slices to get rid of that pie gap that we talked about. But it looks really nice and tender, but it still keeps that wonderful apple slice structure that we want, or perhaps I want. So again, depending on how you want to define a good apple filling, you have various things to adjust. In addition to apple flavor, right, whether they're sweet or tart, not as acidic or very acidic, whether you par cook the apples or not, and then this one we didn't really talk about, but even the thickness of the apples that you slice them at, that determines how fast they cook and how much they release water, determines your outcome. All right, last one. Finally, pie dish material. Doing some observations, I realized that in the kitchen, there are usually about 3 common types of pie dishes out there. One is ceramic, one is tempered glass or Pyrex, and then the other one's aluminum. They all have their pros and cons, right? And on face value, I think price is definitely one of them, and weight is another one, right? So ceramics, I think many cooks use it because they're pretty, right? Especially for Thanksgiving. It's nice to display an apple pie in a beautiful dish, but it's really expensive as a result because they're made very carefully. Tempered glass is much more affordable and therefore much more moderate in weight compared to ceramic. And then lastly, aluminum is the cheapest and the lightest of the 3. But when it comes to baking, it has everything to do with thermal conductivity and the way that they retain the heat when they're baking the apple pie. So when you look at this diagram or this table here, ceramic and tempered glass actually have very similar thermal signatures, meaning that they more or less heat and retain and conduct heat in similar ways. But aluminum has, compared to the other 2, very unusual properties because it conducts heat really, really, really well. But it doesn't retain heat at all. That's why when you put something in the oven and you take it out and there's aluminum foil that you've lined that pan with and you touch that aluminum foil, you don't get burned. But you touch Pyrex or a casserole dish coming out of that oven, you're going to burn yourself, right? That's an example of low heat retention and high thermal conductivity. And that is also seen in the browning of these different apple pie crusts, right? That aluminum with the largest value of conductivity and heat retention browns that pie faster and better than the other 2. But again, it doesn't mean that the other 2 are inferior. It just depends on what your outcome is desired and which one of these materials would lend itself better to that overall outcome. So perhaps if you're looking to make a deep dish apple pie, a nice ceramic one, a ceramic pan, or a tempered glass pan might be good because it will conduct that heat slower for more even browning or even cooking throughout that deep texture or deep height. Or if it's really heavy, right? Like apples can get pretty heavy, and so having a ceramic pie dish might be good so that you don't actually trip over and drop your apple pie over Thanksgiving dinner. Whereas tempered glass is usually desired because it is transparent. You could actually see in real time how that pie is cooking. And then finally, aluminum, it's extremely cost effective, but the limitation is that it browns faster, but that might not be so bad if you're cooking thinner pies. Okay? So I hope all of this goes to show that you can learn a whole lot of chemistry through a fun medium as food and cooking. In fact, this specific lesson plan I talk about specifically with my students, and that's them enjoying the reaps of their labor in the kitchen lab. And if you're ever interested in reading more books about the science of cooking, there are plenty out there and that is written for the general audience that are really, really wonderful. So there's some screenshots down there. But what I want to really leave you on is that I hope this shows you that, again, food is a really great way to relate to everybody, whether in the classroom or outside of the classroom. But for those who are thinking about a teaching career or connecting with individuals, perhaps you might want to choose a different medium. Not just food, but think, reflect on what is something that you might be able to connect with others beyond the classroom. Thank you all. I really appreciate this time.
Thanks for watching. Please like, comment, and subscribe for more content from LSC-Kingwood.